Imagine a new kind of computer. It can try many answers at once. It can solve some hard problems much faster than today's machines. This is not science fiction. It is the burgeoning reality of quantum computing. This revolutionary technology is not just a faster computer. It operates on a completely different set of principles, harnessing the strange, counterintuitive rules at the universe's smallest scales. To understand this frontier, we must leave behind classical intuition and enter the peculiar world of quantum mechanics, where particles can exist in multiple places at once and be mysteriously linked across vast distances. It redefines the essence of information and computation. To grasp the power of quantum computing, we must start with its fundamental ABCs. The first and most essential concept is the qubit. A classical bit is like a light switch. It can only be in one of two definite states, on, 1, or off, 0. A qubit, however, is fundamentally different. It can be a 0, a 1, or a combination of both states at the same time. Think of a spinning coin. While it is in the air, it is neither heads nor tails. It is a blur of possibilities. Only when it lands and we measure it does it settle into a single, definite outcome. A qubit behaves in a similar fashion. Superposition is the formal term for a qubit existing in a combination of both 0 and 1 simultaneously. It is truly in both states at once, with a certain probability assigned to each. This ability to hold multiple values at once is a source of immense computational parallelism. With just a handful of qubits, a quantum computer can represent an exponentially larger amount of information. The third and perhaps most mystifying concept is entanglement. Albert Einstein famously called it spooky action at a distance. When qubits are entangled, their fates become intertwined. Measure one, and you instantly know the other. This profound link creates computational states that are incredibly rich and powerful. Creating and controlling a physical object that can behave as a qubit is one of the greatest engineering challenges of our time. These are real devices. Several methods exist, each with unique strengths and weaknesses. One approach uses trapped ions, individual atoms held by electromagnetic fields, cooled with lasers near absolute zero. Laser pulses manipulate internal energy levels, defining the zero state and the one state. Another approach uses superconducting circuits on silicon, cooled far below deep space, so electricity flows with zero resistance. Engineered energy levels create a qubit with microwave control. Semiconductor fabrication suggests potential advantages for scaling. Photonic qubits encode info and properties like polarization, robust for communication over long optical fibers. Regardless of platform, all qubits share a common enemy: noise. Superposition and entanglement are incredibly fragile. Stray vibration, temperature fluctuation, and electromagnetic fields can destroy quantum information. This destructive process is called decoherence. To combat this, systems live in shielded environments and cryogenic refrigerators at millikelvin temperatures. These machines cool qubits to just thousandths of a degree above absolute zero, essential to preserve states long enough to compute. With the hardware in hand, how do we actually compute with qubits? A quantum computer does not run programs the same way a classical computer does. Instead of a linear instruction list, it applies precise operations to qubits, quantum gates. Single qubit gates rotate superpositions, changing the odds of measuring 0 or 1. The Hadamard gate often starts algorithms, turning a definite state into a perfect superposition. Two qubit gates create entanglement. The C0 flips the target if the control is 1. If the control is in superposition, applying C0 entangles the pair. Quantum gates are reversible, a sharp contrast with many classical operations. A classical AND loses information. Quantum steps preserve it, letting states evolve coherently until final measurement. Workflow: initialize qubits, apply a circuit of gates to explore state space, then measure many times to build statistics. The promise became concrete with breakthrough algorithms. Shor's 1994 algorithm factors large numbers exponentially faster than classical methods. That threatens current public key cryptography if large, fault-tolerant quantum machines arrive. It leverages superposition and the quantum Fourier transform for the speedup. Grover's 1996 algorithm speeds up unstructured search, quadratic but impactful at scale. It finds a target in about SQRT n steps versus roughly n2 on average classically. From theory to reality, modern quantum experiments. In 2019, Google's 53-qubit Sycamore sampled a random circuit in about 200 seconds, a landmark. Google argued classical would take millennia. IBM countered with days using optimized methods. Still, a pivotal demo. IBM provides public cloud access and pursues ever larger, higher fidelity processors. IonQ champions trapped ions, emphasizing fidelity and connectivity. Physicist John Preskill dubbed the current phase the NISQ era. Noisy, tens to hundreds of qubits. NISQ devices test error correction codes, inspire hybrid algorithms, and probe quantum physics. Decoherence, tiny vibrations, thermal jitters, EM whispers collapse fragile quantum states. Gate and measurement errors, even at parts per thousand, compound over millions of operations. Quantum error correction encodes one logical qubit across thousands, even up to 1 million, physical qubits, depending on quality. Scaling demands massive hardware, high-yield chips or long ion chains, dense control lines, extreme cryogenics. Near-term, chemistry and materials, properties of molecules, catalysts, superconductors. Hybrid quantum classical methods explore vast solution landscapes for logistics and design. Meanwhile, quantum-safe cryptography prepares for a future beyond today's encryption.